can see it.
Sounds good.
All right, thank you. All right, our next speaker is Lucas Franceschini, who is at University of Sao Paulo, and before that, he did his PhD at ONERA with the same group as Pedro is in currently. All right, take it away.
Yeah, thank you very much, and thank you very much for having me here. So I'm going to present today the work with title Mean Flow Data Assimilation based on minimal correction of turbulence models and an application to a backward facing step, as Pedro already mentioned. So this work I did when I did my PhD at ONERA on the supervision of Denis Sip and Olivier Marquet. So in that context, we were not. So I'm so sorry. Can you see this bar on the right hand side here? I should be able to hide. Yeah.
Yeah. You're hidden. We just see the slide.
Okay.
Yeah.
Great. So in that context, we were not necessarily interested in the model correction, but we were interested actually into putting CFD together a bit more closely with experiments. So from the CFD point of view, typically we have fields, right? We have fields in function of space, so we have very detailed data. Which are often easier to obtain since we were dealing with Rand equations, which is not very costly. However, those models they could have some errors associated to them, mainly coming from the turbulence modeling. On the other hand, experimental data tend to be more sparse and partial. They are in general more difficult to obtain, or well, to have a very detailed measurements, fancier equipments are needed, and they are often regarded as higher fidelity data. So typically, when those two things do not match, we were interested to take the experimental data and try to put it in the CFD code, which goes in under the name of data assimilation. So this work was published last year in Physical Review Fluids for those who are interested to read a bit more about the work I'm about to present. So more precisely, as I said before, we are dealing with Rand equations, which are the least costly modeling or turbulence modeling that we have, and the most used in industry as well. However, it might have some problems regarding the modeling. So what we should do is to identify within the Rand equation some parameter. So here I have like f of x equals 0 for the baseline model. And then once we include the measurements or high fidelity measurements in our model, we'll tune this f, which are not going to be 0 anymore, so that the solution matches the best as possible with the external measurement. So this is the parts that I'm going to be presenting. Although we should keep in mind that this one is a possible step to doing our augmented Rand model, as Pedro just presented. So more precisely, we're dealing with Sparlow-Tormars model. So here I recall the exact Rand equations. The one where on the right hand side here we have the exact Reynolds stress tensor. And then in the Sparlow-Tormars model, we use the Boussinesq approximation. So we take this whole tensor and we replace it with an equivalent add viscosity. And then this add viscosity, roughly speaking, is modeled by a nonlinear advection diffusion equation. And then the parameters that we were using to tune, actually to modify our original Sparlow-Tormars model were first a volume term in the momentum equation, which is like a Boussinesq correction model. So we are in a way bypassing the Boussinesq hypothesis. So we still have some eddy viscosity there, which is solved by the original Sparlow-Tormars model. But in addition to that, we have this forcing term that's going to be tuned. Also, we have similar to this. We might not do this FU term, but rather introduce a source term in the turbulence model in the Sparlow-Tormars model as well. So the overall goal here is to tune FU or F mu t such that the solution of the Run's equations or modifies Run's equations match the best some experimental data here given by this M, this green M here. So once we construct our cost functional, we see this problem as an optimization problem, which is going to be solved using a gradient-based approach. So we are going to be solving the adjoints and iteratively solve this optimization problem. So quick remarks on the numerical methods. We use FreeFEM, which is a finite elements method code, let's say, open source code. Since we are dealing with a high Reynolds number flows, we need some stabilization, which is not originally in the finite elements method. So we use SUPG. And then for the optimization, we use the low memory BFGS. So a bit more details about the physical configuration we are dealing with. So it's a backward facing step. We are using a DNS as a reference, which was provided by Dandois, published in Journal of Fluid Mechanics in 2007. And the Reynolds number based on the height of the step is around 28,000. So this is the reference truth, the ground truth solution we are going to be using for our studies. And here we have the Sparta-Mara's original solution. So you can see that the recirculation bubble, as Pedro pointed out before, tends to be much longer than an actual data coming from a DNS, for example. So here for the wall friction, for example, we have, sorry, we can see that the recirculation bubble length is around 7, whereas the DNS is around 4. So there is a long wait between those two solutions, so that there is room for data assimilation. So for the data assimilation, we are going to be considering 2 kinds of measurements and see how they perform. So first, we are going to be measuring the whole or dense velocity field, which is indicated by this green, all green in here. So this is just here to mean that we are going to measure the velocity on every point of the mesh, for example. And then we are going to particularize the measurements on vertical strings of points. Okay, so here, for example, I have 3 strings of points in 3 different positions. Each having 10 points, for example. But first, I'll talk about this dense velocity field. So first, the cost functional. So first, I'm going to present how the optimization goes. So the cost functional for the turbulence model correction typically is not fully capable to recover the whole state. So typically it decreases very fast for the first iterations, but then it plateaus and it's not able to reproduce exactly the solution, but it does improve a lot the solution. You can see that the cost functional decreases by an order of magnitude here. However, on the other hand, the boostiness correction, since it's independent, since it's an external force which is free from the model itself, it is free to do whatever it wants actually. So it is able to actually fully capture the states, which means that which can be seen here by this quick or big drop in the cost function. So taking a look more closely now to the fields. So here I just reproduce the DNS and the RANS fields for comparison yet again. So there's nothing new in here. Then if we do the turbulence model correction, we see that the velocity field is much closer to the reference velocity fields coming from the DNS now. However, there are still some errors there. So we can see, for example, for the pressure, wall pressure, we are much closer to the DNS, but there's a gap there. And the same thing goes for the skin friction. So we can see that the recirculation bubble here predicted for the assimilated solution is around 4.5, 4.6. And the DNS is around 4. So there's still a little bit of error. which is completely gone if we do the Boolean correction. So the left-hand side, we basically have the same solution. The CF predicts a very well the recirculation bubble, and the wall pressure is pretty good as well. So taking a closer look now to the, for example, the assimilated additive viscosities. So we see on the top here the original additive viscosity coming from the Spartan Morales model. We can see that its value is around 260, for example. Then once we do the Boolean correction, this value it drops actually. And this is because the role that the additive viscosity was playing before, which is to shorten the bubble, is played now by this extra momentum force. So a part of the action of the Boolean hypothesis is on the forcing term now. However, on the last plot here, since the additive viscosity is the only for the turbulence model correction is the only way to act on the momentum equations, then it has to increase in order for the bubble to be shortened. So it has to increase. So this is why we have like bigger values for the turbulence model correction for the additive viscosity. Taking a closer look now to the forces. We can compare now, for example, the Boolean force correction. This is something that Pedro already pointed out, but for the Boolean correction, the output force that we have, the tuned force, let's say, it's much closer to the DNS. It's a very good match. And the force coming from the turbulence model correction, it tends to be very localized. So you can see that we have like two patches, one red, one blue. High gradient fields and very localized to the separation points. So I believe this could have some implications in the machine learning. So for example, since this quantity here is not, for example, like it's not strong on the bulk of the flow, maybe learning on this kind of quantity should be more difficult than in the Boolean correction one. This is why I think Pedro chose also the second one. So let me now present some results on the point-wise velocity measurement. So I'm gonna go ahead and present two simulations, one for sparse data and one for more dense data. So we see that the error of the final solution is larger for the sparser data than for the more dense data, which makes which makes sense actually. So for this model, including more measurement points in our cost function does improve the solution. However, interestingly, for the turbulence model correction, that is not so much the case. So when we have sparse measurements data and dense measurement data, we have practically the same solution. So we see that the model is almost independent of the number of measurement points that we have. So we say that the model is a little bit rigid, which means that regardless of the number of points, the solution is going to be practically the same. So to try to understand a little bit better this, we resort to a linear sensitivity analysis kind of method. So we are going to see how the model, which is represented by this A operator here, which is linearized, will respond to a very small change in the first term here. Here, the first term could be either the Boolean correction or the turbulence model correction. So we are interested in those lambda squared gains. So how a direction can be modified with a delta, with a variation in the force. So if this quantity here is large, this means that we don't really need a very high modification on the forcing term to go excite this mode. However, if lambda is very low, this means that we need to put a lot of energy into F so that we can move a little bit the states, the final states. And then if we want to look for extrema of this function here, this is the same thing as solving this the following eigensystem and looking for those lambda squared k. Excuse me. So if we plot those for the Boolean correction, we see that they all plateau, right? So this suggests that all directions they are equally controllable or observable. Or if we do this for the turbulence model correction, we see that only a few modes actually can be easily reached. Okay. So this kind of explains in a linear framework why the model was so rigid. It's because there are some modes that are hardly reachable or observable. So in conclusion, we have two models here. Left-hand side is the turbulence model correction, which is not fully controllable, although it does produce a better solution than it runs. One interesting feature is that if we have only a very few points, for example, of data in our so if we only have at hand very small, very sparse information, this model could be interesting because of its rigidity, right? So it goes more faster to the actual closer solution. However, we believe that since the forcing term coming from it is very localized, it should be hard to excuse me, models with it. So if we were to apply the machine learning to this forcing term, since it's very localized, it would be probably harder than the Bostonese correction, which is fully controllable. Allows for a very accurate representation of the solution when enough data is at hand, when we have enough data. And this parameter FU tends to be more spread in space and be very close to the DNS parameter, which is good for machine learning, I believe. So that's it. Thank you.
Great. Yeah, thank you very much. I think that was, I think, quite insightful. There are some questions in the Q&A. Yeah, so first we'll go with how do you tackle near wall flow in your model? Do you use the wall model, or is the model able to capture near wall flow consistently?
Not at all. So I'm using the standard Spark Tomaras. Yeah.
Okay. Yeah, and I had a question. So I think the analysis of controllability or control authority was nice, but it's a balance, right? If you have too many degrees of freedom in the control, then it may not generalize very well, right? So it's something that we should keep in mind, right?
So if we have too many, I'm sorry.
If your model is very controllable,
Yes.
it may also be less generalizable, right? If it sees new things, it may not be able to do well. So it's a balance, right?
Yes, it is a balance. Yeah, you're absolutely right. And yes, so if the model is if we had all the models, all the modes fully controllable equally, it would be at every special points that we measure would be locally improving our model, but not so globally, right? So you're right about that. Yep.
Yeah. So, but it's an interesting balance that we should look at.
Yes.
Yep. And yeah, I
See
think
if we have more questions.
there seem to be no. I mean, there were quite a few that were just answered. So I think, yeah, I think they're good. But yeah, thank you for your talk. So what's coming next? So what are you thinking of once now that this work is done?
That's a good question. Well, one output of this work was the work that Pedro just presented. So we used the data assimilation that I presented for machine learning, which works quite well. Yeah. So.
Okay. All right. All right. Great. So I think if the next speaker can set up. Thank you. Thank you.
Thank you very much.
Yeah. Thank you very much.
Do I have to do anything? So can I? So
you can just stop sharing.